أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم. The today lecture is devoted to the revision of basic concepts of thermodynamics. This is almost the end of this course of thermodynamics, so we want to revise the basics nomenclature of thermodynamics once again. If we look toward the thermodynamics, that is represented by TD normally, that is actually the most basic science and the old science in the history of mankind. One branch of knowledge that all engineers and scientists must have to understand, to grasp, and that is actually the thermodynamics. Because in some sense, thermodynamics is perhaps the most important, and because in every part of life we need to face with thermodynamical systems. So thermodynamics can be basically considered as a system level science which deals with the description of the whole systems and not with the interaction at the level of individual particles. It's like it deals with the quantities like temperature and pressure, average, or a large collection of entities, that is actually molecules and atom. If we separately describe molecule and atom, so it comes in the scope of statistical mechanics, while if you want to measure only the temperature and pressure, so it just comes in the scope of thermodynamics. And it so thermodynamics puts before us some fundamental laws which are universal in nature and which are important for us to deal with. So the nomenclature of thermodynamics is a bit different. We need to know that, and there is several terms that are frequently used in this course. So we need to know the meaning of the terms. Some of the normal terms are the system, surroundings, and the boundary. System is something that is in consideration or in observation. Surrounding is actually the something that is not in consideration, and boundary is the region between the systems and the surrounding. And universe is also the system plus surrounding is the universe of that systems. So we have different systems where we have practically considered the surrounding as the immediate neighborhood of the systems normally. So here we have a simple systems. If we have a block of gold that is placed in water, so the water is the immediate surrounding neighborhood, so it is the actually the surrounding of that. So if we consider the whole beakers that is full of water, so the air surrounding air is the immediate neighborhood, so it is considered to be the surrounding. We have different sort of system that are the open system, closed system, and isolated systems, and these systems are categorized based on their exchange of mass and energy. So there are different particular system. Each of the system is presented here in the table. We have open system in which all interaction is possible. I mean heat can exchange, heat, work, and mass can exchange between the system and surroundings. We have closed system where mass cannot or matter cannot exchange with the surrounding, but only heat can enter or leave the systems. We have semi-permeable system where only certain species can enter or leave the systems. We have insulated system where heat cannot leave or enter the system, that is insulated system. And we have rigid system as well, where mechanical work could not be possible, that is actually called as a rigid system. And we have some sort of isolated system where no work, no heat, and no mass can exchange between the system and surrounding, so that is completely isolated from the surrounding, so that is called as isolated systems. So Matter is easily to understand and include the atoms, ion and electrons, so we can consider that energy may be transferred to the system as the form of heat or electromagnetic radiations. So thermodynamics, we have two modes basically. One is heat and other is the work. So heat and work are the modes of transfer of energy and not energy itself. So this is actually the shape of so once inside the system, the part which came over work and the part which came over heat cannot be distinguished. So this is something what we need to distinguish from each other. And it is clear that matter when added to a particular system brings along with its some energy. So the energy density in the incoming matter may be higher or lower than the matter already present in that particular systems. So we have some list of processes that are possible in thermodynamics, and in some processes the prefix ISO is written, that is normally described to mention that there is something constant in this process. Just like if we consider the isothermal process, then it process takes place at constant temperature. It might be any temperature depending on any particular systems. So if we consider constant pressure, so that is actually isobaric process. If we are heating something in open air or maybe under atmosphere conditions, so and keep the pressure constant, so that is the isobaric process. We have isochoric process if we want to heat up something and seal the cylinder, so that is actually called as isochoric process. There are some reversible processes where we can the system is in close to equilibrium at all times, and infinitesimal alteration of the system condition can restore the universe. So we have cyclic process where the initial and final states are same, and in this case Q and W need not to be zero. And there are some adiabatic process where no heat enters or leaves the systems and dq is zero during the process, no heat is added or leave the systems. So the combination of some processes, just like these are actually individual processes, but in general the combination of two processes is also possible, just like if we have some processes that are reversible as well and adiabatic as well. So temperature actually is when we are feeling I means increasing temperature, I means hot, or decreasing temperature is cold. So that is something, the temperature, which is the measure of the intensity of heat, and heat flows from a body at higher temperature towards a body at lower temperatures. And it describes that if two bodies are in thermal contact with each other and one's temperature is higher and the other temperature is lower, then the heat will flow from the body towards, that is at higher temperature, toward the body at lower temperature, and this flow of heat will continue until both the bodies achieve the same temperature. There are several parameters that are determining the temperature distribution of species across the energy levels. So we need to consider that if we consider various energy levels available for molecules in a system to be promoted, so in case of low temperature, the lower energy levels are expected to be populated more as compared to the higher energy levels. When we heat up the system, so what happen, more and more molecules will be moved toward the, or it will transition will occur toward the high energy levels. So the distribution of molecule across this energy level is given by some sort of equations. There are some few points that are need to be mentioned regarding the different temperature scales. I mean, if you measure the temperature, there are some scales for that, and the common use scales are we have Celsius scale, and we have Kelvin scale, we have the Fahrenheit scales. So these are actually the scales that are used to measure the temperature. and the reading that are taken in one scale system could be converted into other scale system. That is actually is not very difficult. Pressure is actually, if we see, the pressure is actually the, I see looking, that is the pressure is the force per unit area, and it is the momentum transferred per unit area per unit time when we consider the gas molecules. So pressure is related to momentum, while temperature is related to the kinetic energy of the system. Here in this case we are observing that how this gas molecules put pressure on the walls of the container. Heat and work are also important terminology in thermodynamics. Work is actually in mechanics is, if we explain the work, then it is actually the displacement multiplied by the force, or resisting force, and that is equal to W is equal to F cross D, F dot D or F. And work has the unit of energy, that is joule. So work can be expansion work, just like electrical work, magnetic work, and heat is used to in thermodynamics as a tricky term, and that is actually the transfer of energy as a result of temperature differences called as heat. In thermodynamics, heat is not an entity or even a form of energy. Heat is a mode of transfer of energy. Is actually the mode of transfer of energy, and heat is the transfer of energy by virtue of temperature difference. And heat is the name of a process but not the name of an entity. Bodies contain internal energy and not heat. So the flow of energy down a temperature gradient can be treated mathematically by considering heat as a mass-less fluid. That is actually does not make any heat to heat as a fluid. So work is considered to be a flow of matter, and lowering, if we do some work, so what happen if there is a motion of the piston, then some work is done. If you move the piston, if the electron moves, that is also doing work. If you lift up some weight, that is also doing some work. So how heat involves random motion of matter, that is like gas molecules in a cylinder that are randomly moving. If we have water molecules in a cup of water, that is also, and in that way energy can be transferred from one shape into another shape, just like in some cases energy is converted from kinetic energy to potential energy, and or potential energy to kinetic energy. Here we want to describe the reversible processes. Actually the reversible processes is a process where an infinitesimal change in the condition of the surrounding lead to the reversal of the process. So I mean the whole process is reversed, and the place from which where we have started the process, the system come back to that process. If we consider the entropy of this process, then entropy of reversible processes are a constant. But keep in mind, reversible processes are a type of ideal processes which are not found in reality. Normally the process what we are observing in our daily life or in normal thermodynamic processes are irreversible processes where some sort of energy is lost. We have some example of visualizing the reversible and irreversible processes, and there is a simple example of water at minus 5 degrees C, and that is reversible if we convert it twice at minus 5 degrees C. As the same water, if it is converted to it is in 0 degrees C, and that is converted to 0 degrees C, and then it is cool at minus 5 degrees C, and it come back to again it's from minus 5 degrees C, it come back to 0 degrees C. So it's a type of reversible processes. We need, if we describe any particular processes, For that we need to describe the PV diagram, that is called as pressure volume diagram. In most general cases we also use the PVT diagram for any particular process if we describe the state of any particular system. So that is pressure, volume and temperature diagram for that, and that describe all the parameters that are used in that particular process. There are some state functions which are frequently used in thermodynamics, and that state function describe the state of the systems. Just like in thermodynamics, the state function is the internal energy that is represented by URA, and this state function are actually the property which depends only on the current state of that particular systems, and this does not depend on the path used to reach a particular state. So that is why we call it a state function. So a process for which the final and initial states are same is called as actually the cyclic process, and for cyclic process the change in the state of any system or the change in the state function is equal to 0. We have some spontaneous driven processes, and these spontaneous driven processes are like here we have the system is moving from higher potential energy to lower potential energy, or from higher temperature to lower temperature, and this is going to occur naturally because if we see that if we want to bring two objects at different temperature with each other, so it is the natural or spontaneous process that heat will flow from the object at higher temperature toward the object at lower temperature, and it will continue until both achieve the same temperature. Similarly, if there is downhill energy, so if an object is at higher potential energy and we allow it to move, so it will move downhill, and this motion will continue until it reaches the surface. So in that case the potential energy here we see here the potential energy is converted into the kinetic energy. So this is a type of spontaneous processes. Heat capacity is actually the amount of heat that is needed to raise the an unit amount of substance by a unit increase in temperature. That is actually called as the heat capacity of any particular system. So this heating can be carried out at a constant volume or constant pressure, and respectively it is called as heat capacity at constant volume or heat capacity at constant pressure, and its values are mentioned here. We have some laws of thermodynamics that was already described, but we want to elaborate it again. The first law gives us the concept of energy. The internal energy of an isolated system is constant, and a closed system may exchange energy as a heat or work. If we provide energy to any particular system, that might be utilized in doing work or maybe increasing the internal energy of the systems. So there exists a state function U, that is internal energy, such that for any particular process del U is equal to Q plus W, and Q is the heat flow into the system and W is the work done on the systems. So in this case internal energy is a state function for any particular process, and it depends only on the final and initial states of that particular system. So this is some the change in the internal energy of the surrounding will be opposite in sign. So that is del change in the internal energy of the system plus change in the internal energy of the surrounding should be equal to 0. So this is the first law of thermodynamics. The second law of thermodynamics gives us the concept of entropy, and that gives us that no cyclic process is possible such that it can take heat from the from a source and convert it completely into work is not possible. And in other words, you can say no engine is possible whose efficiency is 100%. And the other statement of the same law says that it is not possible to take heat from object at low temperature towards object at heat temperature and give it to the object at high temperature without any expense or any expenditure of energy. So this is something about the second statement of the second law of thermodynamics. So that is the combined Kelvin and Clausius statement of the second law of thermodynamics is if we consider the entropy of a closed system will increase during spontaneous process. So in all natural processes the entropy of the system will increase. So this lead to the increase in the entropy of the universe during any spontaneous processes. So the efficiency, I mean there is some I mean the efficiency of the heat engine become limited, and that should be less than 100%. That is also I mean some restriction on the efficiency of any particular zero. And the third law of thermodynamics says that for substance in internal equilibrium undergoing an isothermal process, the entropy goes to zero at 0 Kelvin, and that is the limit T approaches to 0 del S will be equal to 0. In other words, it can say that the entropy become constant when we are in decreasing the temperature of a body to very low temperature or 0 Kelvin. So for a closed system in thermodynamic equilibrium, the entropy of the system approaches a constant value as the temperature goes to absolute zero. There is also a concept of residual entropy as well, where there is a unique ground state with minimum energy at 0 Kelvin. We have some ideal and perfect gases, and they need to develop the equation for both ideal and perfect gases. Normally we consider the ideal gas, and the ideal gas equation is equal to PV is equal to nRT. So this is something about the revision of the basic concepts of thermodynamics. Thank you very much.